Hello everyone, welcome to a lecture on the topic of solving exponential equations. So in exponential equations, the unknown, or this so-called x we're looking for, is always in the exponent part. And it's not like the linear equations where we have, for example, 2x equals 4, and then we would say, okay, let's divide both sides of the equation by 2, and x would be, of course, 4 divided by 2, which is 2. But now this unknown we're looking for, or this x, is in the exponent part. For example, we have 2 raised to the exponent of x equals 16. So this is an example of an exponential equation, and we need to solve this equation for the variable x. Now, in these kind of equations, oftentimes you can express the right side, in this case 16, as a power with the same base you have on the left-hand side. The base of the power on the left-hand side is 2, and perhaps by a little bit of thinking or trial and error, you would know that 16 is actually 2 raised to the exponent of 4. If it was 8, I would say 2 cubed. If it was 4, I would say 2 squared, which is 2 squared is 4. But now we have 16, so that is 2 to the exponent of 4, which is equal to 2 to the exponent of x, in fact. So I sort of simplify the right-hand side, or express the right-hand side as a power, basically. That's what I do. And then I look at the both sides of the equation, and I notice that we have 2 powers, one on the left, one on the right. And these powers both have the same base of 2. So then I say, okay, I'm asking myself, when would this equality hold, considering that 2 powers are supposed to be equal to one another, and their bases are actually equal. They're both equal to 2. So the logical answer to the question is that the equality will hold only if the exponents are equal. In other words, if x equals 4, then you will have 2 to the exponent of 4 on the left equals 2 to the exponent of 4 on the right, which is 16. And it's very, very common sense or logical. You wouldn't say x is equal to 5, because then you would believe that 2 to the exponent of 5 equals 2 raised to the exponent of 4, which is not right. So the answer is x equals 4. Very easy, very straightforward. But what is going on in your mind right now is the following. You are saying, okay, what if instead of 16, we don't have 16, we have 15, for example? Then we cannot say 15 is 2 raised to the exponent of 4. In other words, the other side, or in this case 15, cannot not be expressed as a power with the same base of 2. So if this is the case, then it's not the end of the world. It is totally okay. We can still solve these kinds of exponential equations. The question is, how? Well, we learned logarithm for a reason. We're going to say if, generally speaking, a equals b, then logarithm of a should also equal to logarithm of b. And this was actually one of the laws. So we can take the logarithm of both sides, log of 2 to the x equals log of 15, okay? And in fact, we can take the logarithm of both sides with any arbitrary base we feel like it. But because on the calculator we have this common logarithm button, so for the convenience purposes, we will just take the common logarithm of both sides. Otherwise, you can take the log of both sides with any base you feel like it. So now we have x times log of 2 equals log of 15 using the power law of logarithm, which we have studied in the past already. So now, if you divide both sides by log of 2, which is a non-zero, real number, then you end up with x equals log of 15 divided by log of 2. Now, using change of base formula, you can say this is actually log of 15 to the base 2, and that's the final answer in exact value. Now, if you want to evaluate this expression, of course, it's not that difficult. You can use your calculator, and you can find log of 15 to the base 2, or you can just punch in common log of 15 divided by common log of 2. You will get the same answer according to the change of base formula. And the answer is 3.906, roughly corrected 3 decimal places. So we did solve this exponential equation. The answer was not an integer like it was before. It wasn't x equals 4, but it was some sort of decimal number. And we did use logarithm to find the answer. Next exercise, the base on the left is 9, the base on the right, there is no base on the right, the number on the right is 81. But everybody knows that 81 is 9 squared. So why don't we express 81 and rewrite it as 9 squared? So 9 to the exponent of 1 minus 2x equals 9 squared. Now you see two powers are supposed to be equal. They both have the same base. So the only time left side would equal to right side is when the exponents are also equal to one another. In other words, 1 minus 2x equals 2, which means that 1 minus 2 equals 2x, and 2x would be negative 1, and x would be negative 1/2, of course. If you plug in negative 1/2 in the equation, so negative 2 times negative 1/2 would be just 1, 1 plus 1 is 2, so 9 squared is 81, that's the left side. The right side is already 81, so left side equals right side, 81 equals 81. So this value satisfies the equation. It's a correct answer. We can even check it, either in writing or even in our minds. Using mental math, we can even check to see if left side equals right side or not after we substitute negative 1/2 for x. We move on to the next question. We see 4 on the left, 16 on the right. So is it true that 4 squared is 16? Perhaps yes. So instead of 16, I'm going to write 4 squared, that's 16. But then it has to be raised to the exponent of x minus 8. So by using the exponent laws from grade 9 math, so I'm going to say this is 4 to the exponent of 2x minus 16 equals 4 to the exponent of 3x. Again, the bases are the same. Therefore, the exponents must be the same in order for the equality to hold. So 3x is the exponent on the left side, and 2x minus 16 is the exponent on the right side. If you set them equal to each other, you end up with a very, very basic elementary school level linear equation to solve. And the answer would be negative 16, needless to say. So we solved this exponential equation, didn't we? Next one has a fraction on the right-hand side. We never had a fraction, but we're not scared of fractions because 1 over 8 is actually 8 to the exponent of negative 1. We need to know exponent laws, from junior grades of high school. Otherwise, we can't do advanced math. So basic things we need to know. So 8 to the exponent of 3x equals 8 to the exponent of negative 1. Again, you see that the bases are the same. So you're going to set the exponents equal, and the answer is x equals negative 1/3. Pretty easy. When you look at the equation, at the beginning you think it's difficult, but when you start thinking about it and applying your previous knowledge and doing the question, you see that it's not that difficult either. 0.5, the decimal number. This was a fraction. This was an integer. This was a fraction. This one is a decimal number. But 0.5 is actually 1/2. Think about it. It is 1/2. And the left side is 2 to the exponent of x squared plus 2x. That 1/2 can be written as 2 to the exponent of negative 1. So you see, every time I'm using the same trick, I'm trying to express two powers on either side of the equation with the same base. That's the trick I'm always using. So this time, if I set the exponents equal to each other, I get x squared plus 2x equals negative 1. And this time, I don't end up with a simple linear equation at elementary school level, like this one we had before, like that one we had before. This time, I end up with a grade 10 level equation. It's called quadratic equation. So to solve this, I write x squared plus 2x plus 1 equals 0. And I can solve this either by using quadratic formula or by factoring. So this is x plus 1 all squared because it is a perfect square. And from there, we can say that x plus 1 equals 0 because when something squared is 0, then that something itself equals 0. Speaking of logic. And from there, x equals negative 1, final answer. Okay, final answer. And finally, this other equation, which is like more complicated, 2 raised to the exponent of 2x minus 18 times 2 to the exponent of x plus 32 equals 0. Perhaps this is the hardest question here. I agree with you. It's a little bit complicated because we have 2 to the exponent of x and then we have 2 to the exponent of 2x. So I'm going to say let a equal 2 to the exponent of x. basically I'm introducing a new variable called capital A. So I'm changing the variable. So the variable is not x anymore. I'm introducing a new variable. I'm changing the variable. I'm saying let capital A equals 2 to the exponent of x. Then in that case, if you square the left side, it will be 2 to the exponent of x raised to the power of 2. And that will be actually 2 to the exponent of 2x. And that's exactly what we have here. Watch, it's right there. So 2 to the exponent of 2x is actually becoming a squared in reality after I change the variable. And then here we have minus 18 times 2 to the x, which is a itself, plus 32. And now I can see the smile on your face because you're saying, well, sir, we came up with a very, very simple quadratic equation that we have learned how to solve it like years ago. And you're absolutely right. And that shows what a fantastic idea this was. This idea of change of variable, this idea of introducing a new variable, and this substitution that I did, is a great idea. So how are we going to solve this quadratic equation? Well, quadratic formula you can use solving by factoring and all that. Let's see if we can do this by factoring. I think we can do it by factoring. We are looking for two numbers that add up to negative 18, but the product is 32. So 2 times 16 is 32. Negative and negative, there you go. They add up to negative 18. So using zero product property, either the first binomial or the second one must be 0, which means that a is 2 or a is 16. Now, some people think the game is over, but that's not true because we still have to do a back substitution at this step. Back substitution, because the question originally was in terms of x. We were trying to find x. We were not trying to find a. In fact, a didn't even exist. A was that new variable that we did create that. So I'm going to say, if you do the back substitution, 2 to the exponent of x equals 2. And here, 2 to the exponent of x is going to be 16. So you see that I ended up with two simple, basic exponential equations. So from the first one, I'm going to say 2 to the exponent of x equals 2 to the exponent of 1. So obviously, x is equal to 1, right? Because 2 to the exponent of 1 only equals 2. And in this other side, 16 is actually 2 to the exponent of 4, I believe, right? Oh, I think we had solved this. What a coincidence, I just noticed. So we have solved actually this equation before. Exactly same numbers, okay? So that means that x is equal to 4 because 16 can be expressed as 2 to the exponent of 4, just like what we said before at the very, very beginning in the first question. So x is equal to 4 and x equals 1. So this is the final answer to the exponential equation that seemed to be like complicated, but now we got the answer. And this equation has two solutions actually. Sometimes we have one solution like before, and sometimes we have like two solutions. And right on the spot, I can give you an example where we don't have any solution. For example, 2 to the exponent of x equals negative 5. Okay, so this is an exponential equation that, believe it or not, does not have any solution at all. So I'm going to say no solution. And the reason why I say so is because the exponential expression 2 to the exponent of x, no matter what x is, any real number you select, it doesn't matter. But 2 to the exponent of x will always be a positive value on the left-hand side. So how could a positive value be equal to negative 5, which is a negative number? So this is obviously and clearly impossible. It's impossible for a positive value to be equal to a negative value. Therefore, conclusion, no solution, period. Okay? So some exponential equations have no solution. Some of them have one solution. Some of them have two solutions, and so on and so forth. Okay? I hope you understood how we solve exponential equations. And I'm assuming and hoping that you'll be practicing a lot to become very skillful in this area. Later in the next lectures, I'm going to teach you how to solve logarithmic equations. Thank you very much.